Hello everyone, my name is Choi. I am a student at Sungkyunkwan University. With the recent Corona-19 infection, the world is not in a normal state. But thank you for attending the ACM-SAC conference. I have researched about text summarization. So today, I present about attention history-based attention for abstractive text summarization. The order of presentation is as follows: introduction, proposed method, experiment, and conclusion. In natural language processing, many studies have been conducted according to the development of deep learning. Text summarization, one of the areas of natural language processing, is the task of understanding long documents and generating summaries. Text summarization has been studied in two main ways. First method is extractive summarization, and second method is abstractive summarization. Extractive summarization is a method of extracting important words, phrases, and sentences from a given document. And abstractive summarization is a method of understanding sentences in a document and generating a novel summary. Extractive summarization is an easier task than abstractive summarization. Abstractive summarization can understand documents and create new sentences. So, abstractive summarization research is a more challenging and focused research area. Text summarization has been developed according to the attention mechanism. Attention mechanism is like this. When creating words in the summary, it is not a way to look at the whole words evenly in the original document, but a way to create words by reorganizing words that need to be more focused. As shown in the figure, when generating the current word in the decoder, here red part, each part of the encoder calculate that needs to be more focused on the input word. Then, obtains the context vector representing the sentence again and generate the word using context vector. But there are two problems in text summarization. First is out of vocabulary, and second is to generate repetitive words. When creating a summary-based sequence-to-sequence model, it predicts the word each time step as the softmax value for existing vocabulary. So, the word not existing vocabulary is not generated. So, Abigail author used attention as two portions. He used a portion of the attention to point the input text as the pointing attention, and the other portion to calculate the context vector as the context attention. Point attention serves the out of vocabulary. And when we simply use the attention mechanism predicting a word, attention value can continue to be high for same word, so it prevents the repeated words from being generated by limiting the words with high attention using covers mechanism. However, it is necessary to create attention every time when predicting words. Common sense: when creating a summary, there are patterns to look at important words or topics in the document. So, attention distribution has pattern, like figure here. It is not calculating your attention distribution every time, but calculating attention distribution using past attention distribution. Here, it captures more effective attention distribution using attention history. So we propose attention history-based attention model. Attention history-based attention model is as follows. It consists of string network, attention encoder-decoder model, and attention leader network, and accumulation network. Attention encoder-decoder model is based encoder-decoder model with attention mechanism. Using all input encoder hidden state and decoder hidden state at current time t, we calculate attention value. And using attention value, we calculate new context vector ct and generate word using context vector ct. This is attention leader network. Because there are some patterns in lighting summaries, there are some patterns in sequence of attention distributions. That is, there can be patterns on where to pay attention next. If we extract such patterns from the history of attention distribution, we can infer the next effective attention. For this purpose, we propose the additional recurrent neural network named attention leader network. This is for modeling the sequence of attention distributions generated at every generation step and capturing the informative patterns from it. The attention leader network starts to work right after the encoding process as the decoder RNN. Here, ART represents the attention history at current time t. So we calculate new attention value using attention history ART. And this is accumulation network. Like the coverage method, we also use the accumulation of attention distribution in the attention mechanism. But here, the pointing attention directly affects the output, but context attention indirectly affects the output. So we need to know the amount of the effective context attention. So we try to infer the effective context attention by adding another component called the accumulation network. We use a single layer neural network with the softmax function to get the effective context attention distribution. We add the pointing attention and the inferred effective context attention into the accumulation vector AT. Since the original attention is divided into the two portions with the parameter of pgen, we also multiply pgen and 1 minus pgen to the pointing attention and the effective context attention respectively. Finally, the accumulation vector is used as an additional input of the attention mechanism, together with the current state of the attention leader network and the current state of the accumulation network. And we train to mix loss function. Generally, models is trained to maximize the probability of the ground truth summary by minimizing the negative log likelihood loss ML. Minimizing the negative log likelihood loss is a good way for training language models, but it does not guarantee to generate correct result since it suffers from exposure bias problem. To alleviate these issues and generate the more informative summaries, we use the reinforcement learning to directly maximize large scores like recent studies. While training with the RL loss can increase large scores of output summaries, it may reduce the readability and fluency of summaries. Therefore, we also mixed both the ML loss and the RL loss to generate natural and informative summaries. For experiments, we used the CNN element dataset consists of news article and human-generated summaries with multiple sentences. Attention included decoder model's architecture has bidirectional LSTM for encoder and LSTM for decoder. Attention leader network has maximum number of input tokens dimensional LSTM, and accumulation network has single layer neural network. This is overall result of baseline methods and our models on the CNN daily mail data set. We report the average F1 score was of large 1, large 2, and large L of up summaries. Bold and underlined numbers are the highest, and bold number are the second. We use the attention encoder decoder model with the pointer mechanism as our base model, and add the attention leader network and the accumulation network sequentially. We also show the result of our full model, which has both the attention leader network and the accumulation network trained with the mixed loss function. Results show that the attention leader network and accumulation network both improved the large scores. Our base model with the attention leader network here plus AR improves large 1 by 0.9 and large 2 by 0.8 and large L by 0.9 compared to the base model. Adding the accumulation network to it here plus AR plus AV, we have an improvement of 0.4 for large 1 and 0.3 for both large 2 and large L score. Using the mixed loss function, we achieved the highest large 1 score and the second best large 2 and large L score. In this experiment, we investigate the attention distribution in the summary generation process to ensure that our method has learned better attention patterns. We evaluate the attention quality by observing the conditional probabilities of post classes in the consecutive words in the output summary. Usually, the words right after a noun are a noun or a verb. So the conditional probabilities of Q noun by noun and Q verb by noun will be higher. We compare the conditional probabilities of the test set and the conditional probability by the attention distribution. The attentions are properly given to the input text. Both conditional probabilities may be very close. We compare the conditional probabilities from the ground truth summary QLEF and the attention distribution by our method QHyper. First table shows the value of QLEF and QHyper for some pairs of postclasses. We evaluate the QHyper with our method, including the attention leader network and the accumulation network trained with the mixed loss function. We choose the most frequent 5 classes among all 42 classes, which are NN is noun, IN is preposition or subordinating conjunction, and JJ is adjective, and DT is determiner, and NNS is noun plural. Each row denotes the given postclass, and column denotes the subsequent postclass. For example, the value of Q noun by noun is 0.1830. We measure the divergence score between QLEF and QHyper with the conditional KL divergence. The smaller the cable divergence score, the closer each other. Second table shows the attention divergence scores of our base model and our full model, including the attention leader network and the accumulation network. We'll report the result of each model trained with the ML loss and the mixed loss. For the base model trained with the ML loss, the attention divergence score is 0.0794, but it reduced to 0.0441 when we added the attention leader network and the accumulation network to it. Using RL training with the mixed loss, it reduced to 0.0422, while using RL increases the divergence score of base model. Here, it implies that the proposed attention leader network and accumulation network effectively work in finding better attentions. In conclusion, we proposed an attention history-based attention model. We capture and use attention patterns in the decoding process of abstractive summarization. Attention leader network is modeling over attention history and relationship between input text. An accumulation network is considering the use of attention distribution in the decoding process. Thank you.